Hello everyone, my name is Santosh Pande. I am from Georgia Tech, and at this UPSLA we'll be presenting our paper called Beacons, an end-to-end compiler framework for predicting and utilizing dynamic loop characteristics. This is a lightning talk for this particular paper. We'll be also having a poster session. So just wanted to give you some highlights of what this work is about and invite you for our talk. So this paper is about the HPC loops, especially about irregular loops. How can we find out their trip counts at runtime using some information? And especially we focus on irregular loops. They are very hard to analyze, and we do not know many times their exact execution characteristics. And the examples of these loops are while loops, or those which have multiple exits, which with break statements and so on. So surprisingly, you will see that almost 55, more than half loops, 55 to 56% loops fall in this category in many HPC codes. And because of the lack of trip count knowledge, one cannot accurately determine the underlying data footprints, timings, and in fact, some of the transformations could also suffer without such information, such as shorter loop being preferred to be the outer loop and so on. Now, what are the important questions that are answered in this work with regard to such loops? So the biggest question is, how can we predict the dynamic trip counts of an instance of an irregular loop execution just in time before its execution? So note that in a given benchmark or in a given application, a given instance of a loop means the loop executes probably multiple times during the HPC code's execution, and we are interested in finding out what are the trip count in a particular instance. So how do we do this? Well, you can see that many of these loops, which are irregular, are still entered through certain dynamic states of key variables that affects their termination condition and therefore the trip counts. What we do is we use a combination of compiler analysis to determine such variables which determine such a state. And using ML, we capture and correlate the state with the trip counts. The generated model sits at the loop entrance and at runtime, therefore predicts the loop trip counts. So what do we do with such information at runtime? That's the next question that is addressed in this work. Well, as you can see that many of these loops carry very heavy cache activity, have large footprints, execute for very long times, etc. Knowledge of exact trip counts really helps to determine the resource requirements as well as their duration of execution. And we use this information to aggressively schedule the different independently executing processes on multi-core machines. For example, we solve the problem of locality by avoiding cache-heavy co-execution when there is a large amount of overlap between these processes. Whereas when the overlap is small, we maximize concurrency and we try to therefore balance between locality as well as concurrency to get the best schedule done. It may be noted that the sharing of such resources aggressively and better schedule really leads to very high throughput. And we see that in this particular case, we have a throughput of 2x over a widely used CFS scheduler, which is in the Linux distributions. And we also have demonstrated that over a reactive scheduler, which does not manage this information proactively. As indicated earlier, we have a huge gain of 2.62x. So what is it that is at the heart of this? The heart of it is about accuracy of prediction of dynamic trip counts. And we have about 80% accuracy there, and therefore similar accuracies on the memory footprints and so on. and therefore the cache activity is very accurately managed because of this information. Well, those were the highlights. There are a lot many details to be seen. So please come to our session on compilation and optimization at room 12 on Thursday, and also the poster session on Tuesday evening. Thank you. See you then. Bye-bye.